Everyone thinks a robot grips by squeezing hard. But watch this arm crush a soda can, then hold a raw egg without a crack. It feels 5 grams and stops in 5 milliseconds. Here's the trap. A plain gripper only knows position, open or closed. It shoves to a fixed point with no sense of touch, so it treats an egg like a steel bolt. That's how production lines crush fruit, shatter glass, and dent electronics. The real puzzle, closing the loop between feeling and stopping faster than the object can break. Start with the skin. On each fingertip sits a tactile sensor, a patch that turns a squish into a number. Press it and the surface deforms. The sensor reads that deformation and outputs a signal. 3 flavors do the job. Capacitive pads measure how far 2 plates get pushed together. Piezoresistive pads change electrical resistance when squeezed. And optical sensors like gelsite are a soft rubber pad watched by a tiny camera from inside. The camera sees the exact dents an object presses into the gel. Here's the key move. That pad is split into a grid of tiny pressure cells called tactiles. Think pixels but for touch. Each tactile reports its own little force. So the gripper doesn't get one blunt total. It gets a whole map. How hard and exactly where. How sensitive. The best of these feel forces of just a few grams. Roughly what a single raisin weighs resting on your fingertip. That's already in the neighborhood of a human fingertip. And it doesn't only answer how hard am I pressing. It answers where is the contact and is the push even or lopsided. But a map of touch is useless if nobody reacts to it in time. So who's reading this map and how fast can they act? Now the reflex. The touch map runs a fast loop. The sensor reads, a controller decides, the motor eases off over and over. Picture the 5 millisecond budget as 3 quick beats inside 1 blink. Beat 1, sample the sensor. Beat 2, compute the response. Beat 3, back the motor off before the force crosses the line where the object breaks. Why so tight? An eggshell under overload gives way in tens of milliseconds. If your loop is slower than the shell, you lose. The crack wins the race. So the whole reflex has to finish inside a few milliseconds, again and again. This is the real split. A blind gripper runs open loop. Move to this position full stop, no matter what's in the way. A feeling gripper runs closed loop. Squeeze until I feel the right force, then hold there. Same motor, same jaws, but one is deaf and one is listening. The listening one is checking its own touch hundreds of times a second and correcting on the fly. That's what turns raw squeezing power into a careful pinch. But even a perfect pinch has a sneaky failure. What if the object doesn't break, it just quietly starts to slide out? Catch it before it falls. When an object begins to slip, it doesn't wait politely. The surface sends out tiny shivers. Those are micro vibrations, plus a sideways tug the sensor reads as shear. The fingertip feels that faint tremble the instant sliding starts. Here's the clever part. Instead of clamping as hard as the motor can, the gripper hunts for the minimum grip that stops the slip. Just barely enough and no more. It squeezes softly, waits to feel a shiver, and if it feels one, it nudges the grip up a notch. Slip gone, then hold right there. No slip, no extra force. That light touch is the whole trick. Why beat a fixed setting? Because a fixed force is a guess, and the gripper doesn't know what it's holding. A full water bottle and an empty paper cup need wildly different grips. Set the force too low, the bottle drops. Set it high enough for the bottle, you crush the cup. By reacting to real slip instead, the same hand adapts to any weight and any surface. Slick glass, rough cardboard, without being told a thing about them in advance. It reads the object by feel live. So touch handles breaking and slip handles dropping. What handles the split second the electronics can't cover? Let the hardware help. No electronics react instantly, so smart grippers give the machine some physical give. That give is called compliance. The finger flexes and molds around the object instead of pressing straight through it. Soft grippers use bendy, air-filled, or rubber fingers that wrap a shape like a hand cupping a peach. Under-actuated fingers have joints that fold to fit on their own, with no motor per knuckle. And series elastic actuators tuck a spring between the motor and the fingertip, so a sudden jolt gets soaked up by the spring, not slammed into the object. See how the two halves team up? The soft material absorbs the first shock in the physical world, buying a few precious milliseconds. The fast electronic loop then fine-tunes the grip. Hardware cushions, software corrects. But there's a real trade-off, and it's worth naming. A softer, springier gripper is gentler and more forgiving, yet it's also slower to respond and can't hold as much weight. A stiff gripper is strong and quick but far less mercy. So you match the tool to the task. Soft, cushioned hands for eggs and ripe fruit. Stiffer, sensor-heavy hands for a fast line handling sturdier parts. There's no single best gripper, only the right give for the job. Now the whole trick clicks. The fingertip feels down to a few grams and maps exactly where. The reflex loop closes in 5 milliseconds. Red, decide, ease off, beating the shell's own breaking time. The grip hunts for the minimum force that stops any slip. And compliance, the physical give, cushions the split second the electronics can't cover. 4 layers, 1 careful hand. This is running right now today. It's how warehouse arms pick a mixed bin, a can, a bag, a light bulb, back to back. It's how machines sort ripe fruit, handle food, and place delicate electronics without a scratch. And here's the bigger arc. For decades, robots were caged behind fences because a blind, forceful machine near people or fragile goods is dangerous. Touch is what lets them out. A robot that feels grams and reacts in milliseconds can finally step into the messy, unpredictable human world and handle it without crushing what it holds. So the whole answer is small and fast. Feel a few grams, react in milliseconds, and press with the least force the job allows. That's how a robot stops crushing what it holds. Which opens the next question. If a fingertip is really a grid of touch pixels, could a robot one day feel more than your own hand? We'll open that box next.